Go out and help someone is the best we can do. There's someone who needs someone to help. You might too.
Well, it looks like it's a little after 12, so I think we'll go ahead and start. I want to welcome everybody for being here and thinking about the environment and our Earth. So I wanted to welcome everybody to this lunchtime environmental talk. Thanks for having your lunch with us. This is for people who are interested in learning more about Mother Earth and the environment. These talks are sponsored by the Brazos Unitarian Universalist Church. And you may ask, why would a church sponsor something like this? Well, the Unitarian Universalist religion is based on 7 principles and 6 sources. The 7th principle is show respect for the interdependent web of all existence. So in most people's minds, that means the environment. And we also seek knowledge from 6 sources. And interestingly enough, some of the sources include science and education, making educated decisions. So this is a topic that many people are concerned about, climate change and just water conservation and pollution. So we thought we'd start these talks as an outreach program. We've had some really interesting talks so far. Today's talk is going to be recorded, or is being recorded. So I just want to make sure everybody knows that. And we will have this talk on the website, and it's brazos-uu.org under the social justice title. These talks are going to continue, and they'll be on the 2nd Thursday of each month. And we have some very interesting talks coming up on March 25th. Professor Alan Pepper from TAMU Ecology and Evolution Biology will give a talk on global weirding, expected but not so obvious consequences of climate change. And he will explain the basics of global warming as well as its consequences. So at Texas A&M, they are starting classes. They're instructing some of the undergraduates on scientific things such as carbon dating, global warming, evolution, sort of the basic type of things. And he does give this class to the undergraduates. And then in April, the 2nd Thursday is April 8th, Professor Alfredo Garcia from TAMU's Industrial and Systems Engineering. Well, his wife actually volunteered him to do this because there was a conversation on next door in my area about the blackouts we were having and the grid. So his title is Regulatory Design and Rare Events. And he'll describe the market design features that currently render Texas electricity market vulnerable to rare events and catastrophic consequences, such as the recent polar vortex. So a lot of this is a result of global warming and climate change. If you would like to be on our mailing list, just send me your email address in the chat. My name is Pam Johnson. And today, I'm really excited to have Professor Gunnar Schade. I hope I pronounced that right. He's from Texas A&M in the Department of Atmospheric Science. And the title of his talk is, Let's Talk About Climate Change. Climate change is the ultimate test for humanity. Are we smart enough to prevent the collapse of our own society? And I'll hand it over to you.
All right, I think you have to allow me to share screen.
Okay, I'll get on there.
Yeah, I can share screen now. I got
Okay, good. And everybody should put it in the speaker mode and make sure you are muted.
You can keep your videos on. I don't have a problem with that. I actually like to see any responses from the audience. What I'm going to be showing you actually is, I cheated a little bit with the title here, in that I'm not going to have a ton of slides about the energy transition. It's not my main research topic. So I'm going to start out with a little bit of science. You may hear more of that, as I just learned from Pamela, next week. So I'm only going to give you snapshots, okay? I'm going to talk a little bit about history weaved in to this. And the main thing I want to do is I want to talk about the future because it may be very, very exciting. There's lots of things going on. And so this is where we come in with the energy transition. So that's going to make a huge difference in the next 2 decades. So before we go there, a few things about science. And actually, I've chosen to use quite a bunch of slides. And I'm glad that Pamela mentioned this, of from courses that we teach here to the undergraduate students. So I've been teaching climate science for almost 30 years now. And the basics have not changed. So what we knew at the end of the 1980s is basically what we know today, with a few additional pieces of knowledge. But everything that we needed to know in order to act, we actually knew by the end of the 1980s. And if you're interested, contact me. I can send you a link to some interesting history from the 1980s that was published in the New York Times Magazine a few years ago. That really goes into detail of what the discussions were in the 1980s. So fascinating piece of history. You have to be patient because it's book length, more or less. All right, let's dig in here. I want to give you a brief idea of what can change Earth's climate. I also want to mention in between how we know this. It turns out that we know much more about this than is commonly communicated. This is one of the problems with misinformation, right? Scientists, in conjunction with journalists, often have a hard time communicating this to the general public. Suffice it to say, we know so much that it is overwhelming. One of the things that often gets misunderstood, what the time scales are, right? It turns out that climate changes from millions of years to millennia to decades. So there's a number of time scales in there. And if you want to misinform people, you're going to mix these up like crazy and tell people that, you know, this and this is true, although it's all bogus. How do we know what actually happened in the past versus what happens now? There's plenty of things that we have access to and have researched in the field of climate science in the last 30 years that is fascinating from a number of different aspects. It is amazing. Now, what are the causes of climate change? This is basically it. This is the short list, so to say, right? We have continental drift. You've all heard of that. We have changes in the solar output. We have changes in how we distribute the solar radiation on Earth. And I'm going to show you this, the famous Milankovitch cycles. You've probably heard of that. And then, of course, we have the composition of our atmosphere, especially the greenhouse gases in the atmosphere, which act like a blanket on us at the surface. So this is the base of modern climate change. And then we have one of the favorites of the misinformers, which is internal variability, right? Claiming that because we have some internal changes in the system that this is why the climate is changing. All right, I can quickly dismiss continental drift because it is so slow, right? Continents nowadays move maybe 1 to 2, at most 3 centimeters a year. So the change that comes from that plays out over millions of years. And in what you see in this graph here, and let me get my fancy mouse here, that is going to be red like a pointer, yeah? You see this millions of year drop, yeah, from 50 million, almost 50 million years ago to 20 million years ago. There is this very, very slow drop in atmospheric carbon dioxide, which we have a pretty good idea of nowadays. And we know this happens through some very, very slow chemistry, which is called the weathering thermostat. This is essentially the, because CO2 is a very weak acid, it dissolves rock over time. When you create new rock, like when India collided with Asia 45 million years ago, we built the Himalayas. And that mountain building led to so much rock being exposed to the atmosphere that it very slowly sucked the CO2 out and led to a very long-term cooling of the planet. But that's way too slow, right? The changes we're observing are of order years and decades, centuries these days. So millions of years slow changes do not do the trick. What about solar changes, right? What you're looking at here is actually what we call TSI, total solar irradiance, which is measured by a satellite. We have a geostationary satellite in orbit that looks at the sun. In fact, if you ever travel to Boulder, you can go into the National Center for Atmospheric Research, and they have a little monitor that shows the camera picture from the camera looking at the sun. So when the sun is actively having so-called sunspots, that's the phase when its output is higher, right? You can watch the sunspots on that monitor in Boulder. Sometimes they put it on the webpage and you can watch it live there too. So high sunspot numbers is the maximum, low sunspot numbers is the minimum here. But look at the numbers, right? So misinformers will show you the wrong scale on this graph. They will show you sunspot numbers or something made up on the y-axis here and not tell you that the change from this solar cycle that you're looking at here is less than 1 per mil of the output of the sun. It's so small that it cannot really create any climate change on Earth at this time. And we have absolutely no indication that this cycle is actually having any effect of climate on Earth at this point in time. When you look at the long-term trend from this, right, since the 1970s, there's not much at all. If anything, it seems to be slightly going down, while the temperature on Earth is going up. So that cannot explain what's happening right now either. Now, what about the famous Milankovitch cycles? This is hard to teach, I can tell you, and you probably won't leave today with a very good understanding of this, but you know, watch it again afterwards. Maybe you'll get a better idea. Now, it turns out Earth is not going around the sun in a circle. It turns out it's an ellipse. There are times when we are further from the sun and times when we are closer at the sun. And actually right now, we are closer to the sun when it's winter in the northern hemisphere. And we're further away when it's winter in the southern hemisphere. So this is quite interesting. It leads to a very small change in when you get that energy from the sun hitting the northern hemisphere or the southern hemisphere. We call this the eccentricity. And it changes. It has a very long cycle, right? So it gets more elliptic and then closer to a circle within about 100,000 years. So it's a very, very slow process. A little bit faster is when how we tilt, right? You all know that we're tilted. And so in the northern hemisphere summer, if my head is the sun, right? Northern hemisphere summer means my pinky, I'm sorry, that's my pinky. No, my index finger is pointed towards my head. Northern hemisphere summer, right? If I go around, northern hemisphere winter, now the southern hemisphere, my wrist, right, is pointed towards the sun, and so we are in northern hemisphere winter. Now it turns out that this tilt is also changing over time. We tilt more towards the sun or less more towards the sun. So if we tilt more, we're getting more radiation towards the North Pole. That matters a lot because there's ice at the North Pole. If I put more solar radiation on that ice, it melts more every summer. So this matters. This is called obliquity. And the last one is what we call procession. Anyone who's ever played with a little top on the table knows what precession is. Yeah, it's also called wobble, right? So if this is the axis, the top is spinning around. Yeah, often this axis does this. Yeah, and you get all dizzy watching it. Yeah, so that is what we call precession. Right now, our axis of rotation is pointing at the North Star in the sky. Right, that's what we navigate by, or what we used to navigate by on the ocean. Right, we knew that north is where the North Star is. But it turns out that in a few tens of thousands of years from now, that Earth's axis is not going to point at the North Star anymore. It's going to point somewhere else in the sky. And so seafarers in 10,000 years from now cannot use the North Star anymore to determine where north is. So this is what that precession means. It turns out that these three cycles combined actually are the causes of what we call the ice ages. Yeah? This popularly understood as the ice ages. So what this graph shows is the modern times on the far right. Yeah? And we're going back into the past about 400,000 years. And you can see that at about every 100,000 years or so, which is that eccentricity cycle. We get a warm period, which scientists call the interglacial. So the last interglacial was about 120,000 years ago. And a lot of things changed at that time. And the last glacial, this is down here, about 20,000 years ago when that ended. This is when we had ice sheets over North America that reached down past the Great Lakes, right, with kilometers of ice above New York. So that was a very different time on the planet. And that was about 8 degrees Celsius colder in Antarctica than today. That translates to about 5 to 6 degrees colder planet during the bottom here of that ice age. So globally, it was about 5 to 6 degrees Celsius, about 11, 12 Fahrenheit colder than it is today. So we can be happy that we are living here. In fact, all of humanity, all of society actually developed within that last 10, 20,000 years, right? There were humans on Earth before who lived through that interglacial and that glacial period, but we were nomads. We had very little language, right? So we were cavemen, basically. So all of society developed in these last 20,000 years in that warm period. That's quite a stunning revelation. You can also see these other cycles, by the way, in this, right? It's quite amazing. Now, what has happened in the last few hundred years is that we got some dramatic changes to greenhouse gases in the atmosphere. And this is what scientists are now virtually sure of is what's driving our current climate change. The changes over the last few thousand years to the abundance of these greenhouse gases in our atmosphere has been traumatic, which is why we're now talking about the age of humans. And you might have heard the scientific terminology that's used for that. We call this the Anthropocene, right? Well, anthropogenic means man-made. So this is a man-made change that is currently dramatically changing the surface temperature of Earth, because these greenhouse gases act like a blanket. You throw an extra blanket on, you're going to be warmer. Now, how do we know this? There's a very simple experiment that you can do. Not with another planet, we only have one, right? But we can recreate the planet in a computer program, which is called a model of the climate. And when we do that, we get all sorts of results. All these squiggly lines you see up here, that's an individual computer model run. And we do thousands and thousands of these, and that's how many lines you get there. What this shows, though, is that we can recreate the climate of the last 150 years if we use all the parameters that we know affect the climate. If we leave out the effect of greenhouse gases, that's the result that's in the middle of this graph, we cannot explain the observed warming, which is this black line, right? If there were no effects of greenhouse gases on the climate, our climate should have been pretty stable over the last 200 years or so. But that's not what's the case, right? We have increased the greenhouse gas, and the greenhouse gas impact is on the bottom. When you combine the middle and the bottom, you get the top, and you get a pretty good match. And this is why scientists are convinced that only greenhouse gases really can explain the recent warming of our planet. And we have plenty of fingerprints that point to the greenhouse gases, and I'm only listing a bunch of them here. That's not a complete list, but basically, these are all fingerprints that point to greenhouse gases and not any other effect as being the current driver of climate change. And this, as I said, was known 30 years ago. So this is not new. Last, I want to quickly show you this animated GIF here, right? So what you're looking at is essentially the last 50, 60 years of average global temperature and the wiggles that are in it. Yeah. So the ups and downs you see here, that is what we call internal variability, right? So it's not like every year is getting warmer than the year before. We see a lot of ups and downs in that. And we understand that as what we call internal variability. One of the most important drivers for that internal variability is understood to be the ENSO. And you've heard of that. The EN of ENSO stands for El Nino, right? You've all heard of the El Nino cycle. The red data points in this plot show you the El Nino years. The blue ones show the opposite phase, which is called the La Nina phase. And the black dots are the neutral years. And you can see all of them have essentially the same trend. All of them are getting warmer. The El Nino years are hotter, the La Nina years are hotter, the neutral years are hotter, such that in combination, the temperature is going up. So the underlying trend in this graph is the effect from the increased greenhouse gases. But that doesn't mean that one year is always going to be warmer than the next year. The other internal variability that you may have picked up from this graph is volcanic eruptions. That's a different effect. And so if volcanism is very active in certain years, it tends to cool down the Earth a little bit more. If it's absent for a longer period, that tends to not affect the climate. All the other effects then drive the climate. I'm going to skip this in the interest of time. So what I quickly try to get through here is that we can exclude all the other potential drivers of climate change. The one driver that we know is currently going to change our climate, and it's doing so very rapidly, more rapidly than any other known process that we have access to. And internal variability, the noise that we observe, cannot explain the current warming. It's just noise in the system. And it's short-term noise, it's long-term noise, but it cannot explain away the greenhouse effect. All right, so it's getting warmer. That's not a biggie, right? It's not anything worse. What you hear a lot of people say is that, all right, I'll accept that it's warming, but it might be natural. We'll adapt to it. It's not a big problem. Well, this is the thing, right? It actually is a big problem. Both the speed of the warming and the magnitude of the warming are completely unprecedented in Earth's history. So one of the things, and I'm just cherry picking one here, is that we're going to get a lot more severe weather, or what scientists call extreme events. Heat waves and floods belong to that. Sea level rise from a geologic point of view is also an extreme event, although it happens much more slowly. It turns out that our society is just not built for these changes, right? Our complete human society on Earth is built for a stable climate. we have not taken into account a rapidly changing climate. So we build on the coast without essentially taking account of sea level rise. Floridians get to see that firsthand, right? They have lots of what's called fair weather flooding these days, where the sea level at high tide just comes in and floods the street of Miami. It's a normal occurrence these days. So over time, of course, that leads to Miami going to be uninhabitable. And that, in fact, is likely going to happen sometime this century. So it turns out that when you look a little closer at this, it's not going to, lead to the extinction of the human race. It's not going to eliminate all life on Earth, right? Earth will be fine. Earth will be completely fine. It's human society that we're worried about, okay? This is why I was preceding my talk with a little title of, will we be smart enough to stop this effect that essentially kills our society as we know it? And how will it do so? Well, you've seen last month how this works, right? An extreme weather event knocking out power, which has so many add-on effects that a seemingly small thing as rolling power outages has an enormous effect, potentially, on society itself, right? Our food supply, even though we have enough food, is going to run out within days, right? Because we build our society of just-in-time delivery. If an extreme weather event puts that out of business, that just-in-time delivery, people will go hungry. People will be out of water, right? So the societal add-on effects of a seemingly small event will be enormous. If you have more than one extreme event there in a year, this can be catastrophic. So this is what we're worried about as scientists. And I want to give you one example of this. This is the forecast of what's going to happen when we're doing only what's currently planned, right? So this is a scenario of global warming in the year 2050. That's on the upper right here. Yeah? How many heat waves are we going to get in the year 2050 if we continue on the current path, which you could characterize as a moderate response of humanity to global warming, right? So we're going to not put out as much carbon into the atmosphere as possible. We're going to limit ourselves just a little bit. Yeah? This is what that moderate mitigation stands for. Yeah? It turns out that even in that scenario, if we do a little bit, we're going to have whole swaths of the tropics be essentially uninhabitable by the year 2050, because they will experience near continuous heat waves in some areas, like in close to the equator in South America, close to the equator in Africa, and over in Indonesia. Yeah? Even in large parts of the US, you will get so many heat waves, right, on order of extreme heat days of order 100 or so per year, that this is potentially having catastrophic effects on society, right? We can deal with a heat wave that's several days long. We cannot deal with 5 heat waves a year that are several days long, right? That can have very strong impacts. So no, this is not going to just be no biggie, right? A lot of people who currently live in these areas will migrate north. And migration is a huge factor in human societies. So how long have we been knowing this? Well, basically for a very long time. Yeah? All the science basically has been in for many, many decades. One thing I want to point out is that we have computers for about 60 years now, and they were used early on at the end of the 1960s into the 1970s to create these climate models. And since the mid-1980s, so for almost 40 years, we've actually had forecasts of where we're going to go. And I'm not showing this, but it turns out these forecasts have been correct. We now have, right, several decades of data, And they are spot on. Basically, the amount of climate change that has happened was correctly forecasted already in the 1980s. All right, so what do we do? Okay, so now we're coming to what's actually available to us. What can we do to make this stop? What scientists have been saying for a very long time is that there's a very easy way to stop this. Stop increasing greenhouse gases in the atmosphere, okay? Which means you have to stop all man-made greenhouse gas emissions. That's not easy, okay? But is also not difficult in the terms of that we have all the technologies that we need. What this will do is it will stabilize the climate. It will not cool it back down. So in other words, you know, you're not going to get a hump and then it's going to cool back down. No, you're going to go up, and as soon as you stop emitting, you're going to level out. And then that's the climate that but definitely all future generations will have to live with, right? The climate will just stabilize. It will not cool down. At least for the next hundreds of generations, it will essentially remain the same. It takes tens of thousands of years to remove the amount of carbon dioxide from the atmosphere naturally, which we have put in the last 150 years, right? So in other words, the last 3 generations, including our generation, has messed it up for the foreseeable future. Well, the argument has been made that in order to stabilize the climate, so to do this, first we have to deny that there's a problem. I put this in parentheses here because arguably you can do something about the problem, even while you keep denying that there is a problem. This has been variously suggested, and sometimes it works out, right? So right now, to give you an example, we're seeing that the legislatures in Florida actually are responding to sea level rise. They are accepting that sea level rise is happening, and they are acting accordingly. They're still in denial, though, that sea level rise is due to the warming of the planet, right? So yes, you can do something about it while you still deny what the cause of the problem is. It is possible. How do we stop the greenhouse gas emissions? Well, this is the exciting part that we hopefully will become a big part of ourselves, namely transitioning away from all fossil fuels. That doesn't mean we're not going to have fuels anymore, right? We can make fuels from other things if we need fuels. Biofuel technology, for example, has been a big research topic. Yeah? All right, let's do it. Let's do it. And actually, this is the interactive part with you. I'm going to show you a few more slides as an intro. And then what I want to do with you is I want to look at what's called an integrated assessment model. Yeah, this is what scientists, in fact, mostly social scientists, economists use as a tool to determine, you know, what is going to happen in society if we do X, right? If we don't do X, if we do Y, how is that going to affect society, right? Economists do these kind of things all the time. In physics, right, we have physical laws, right? That if I do this, if I, you know, shoot a cannonball over there, I know where it's going to come down, right? With the economy, it's a little bit more tricky, right? But because what we're trying to predict is human behavior. Nevertheless, you can build these models because we can input what we know scientifically. We can input the technology that we know of. In fact, we can even input some idea of a new technology that we invent. Okay? We can input all the man-made economics that we know, right? We can model society as a capitalistic society, and we know how economics works. And last but not least, we can also put in some human behavior, right? We tend to be a reasonably good predictor of human behavior, right? At least economists think so. Before we go there, though, let me tell you about some really cool recent developments. Okay, so this is the really exciting part here. It turns out that renewables have become incredibly cheap. In fact, they are now the cheapest energy technology in most places on Earth. There's a few places where you don't have a good resource of wind or solar energy because it's cloudy most of the time or it's not windy enough, right? So that you're not producing enough electricity from solar and wind. But those regions turn out to be limited, either because not a ton of people live there, or because that limitation is not going to be present all year round. And so the resource, be that wind or solar, is actually pretty good. It turns out most of the planet is water, right? So we have a lot of coastlines, and most coastlines are windy. So basically all coastlines on Earth are good resources for wind energy. So these two energy sources have been built out in the last 10 years to an incredible amount, and their price has come down by a factor of 10 for solar energy, and still by a factor of 8 or so for wind energy. So you can see that the costs of wind and solar are now cheaper than even the most efficient gas-fired power plant out there. And it doesn't matter what political leaning you have, all US states have recognized that, right? Iowa, not known as a liberal state, right, has built out wind and solar in a huge fashion. So money does make a big difference. And this is why a lot of utilities have a very hard time nowadays to go the old-fashioned way, right? Just build that new fossil fuel-fired power plant, because they're getting offers from the renewable power industry that is going to give them the same amount of electricity they're planning for, because the utilities plan for the future, and it's going to be a factor of 2 cheaper in some places than the cheapest gas they can get. Okay, so what do, right? As when a lobbyist from the oil and gas industry comes and says, we're going to give you lots of cheap gas here, you want to do that, right? But you have an offer that's much cheaper. So it turns out this is a very rapid development. And you hear lots of naysayers, though. And why do you have them? Because they use 10-year-old data, right? Even the International Energy Agency is using outdated data all the time for this, right? So this development has been coming in under the radar. Most of you have probably not heard about it because it's just not front page news stuff. So here's another example, right, that compares this a little bit more closely with other sources of energy, right? Coal prices have not changed, right? It's because the price of coal is not changing, and it cannot drop. We don't have new coal technology. We pay the same price for coal, so why would coal get cheaper, right? There is no what's called learning curve for coal. There is very small learning curve for anything else but wind and solar, okay? And keep in mind, one of the big factors here is that as we build out more, this learning curve keeps going, right? We have free energy. Wind and solar is essentially free. So all we have to improve is the technology. And as that keeps improving, because we're installing more, so we're learning by doing, the prices keep coming down. This is known as Moore's Law, right? As you make stuff and you put it out and you use it, you learn from it. And the next generation is cheaper. The learning curve for solar and wind has been incredible, and that's why their prices are so low nowadays. It turns out, yes, the corporate world is actually driving this. The corporate world is buying this, and venture capital is paying for it for the most part. So both of these type of developments have been going under the radar more or less completely. Now, when do we expect this? How do we expect this to go down? Oh, I had a question here. Why did nuclear go up in cost in the previous slide? Okay, let me go back for a moment. That's a good question. Why did nuclear go up in this? This is not, nuclear has no learning curve either, or better say that they don't have it yet, because we're still in terms of nuclear construction, we're still using old technology. The new so-called modular nuclear reactors have actually not proven, have not been put out. They have not been built. They have not had a chance of having a learning curve yet. So it is possible that once you actually use it, once you build it and use it, and you learn from it, the price may come down. But the nuclear has the continued problem that due to the safety issues, it's extremely expensive. So there's a bottom basically below you which you can't go because you have to pay for all the safety features, right? No such thing with renewables. All right. So when do we get the super cheap energy, right? So these are the decay curves for the price. Actually, these are based on the past development. These are conservative estimates of how the price of solar is going to develop in the next 30 years. And what you can see here, I hope this comes out on your screen, there's a range in between here of prices from about 3 to 5 cents per kilowatt hours that we're currently paying for fossil fuel power, of the cheapest fossil fuel power that is there, right? So these are established, written off old power plants, coal and gas, that can give us really cheap power because they've been on the market for so long. Yeah? It turns out that we can shut them down. In about 10 years from now, we can shut most of these down because even though they are so cheap, solar will become so incredibly cheap that's going to be cheaper to build a new solar power plant than to use the existing old fossil fuel power, even at low fossil fuel prices. It's going to be incredible. All right, let's go there. What I mean by that is this is actually a web page and you can use this yourself. What we're going to look at here, and I'm going to share the screen. This is what this looks like. Yeah. This is the integrated assessment model that lets you predict the future, so to say. Right? There's a lot of what is called levers on here. They are on the bottom. On the top, what you see is what we're currently getting our energy from, and what this development of energy sources leads to in terms of greenhouse gas emissions to the atmosphere and the amount of warming we get from this. So this is pretty similar to this example I showed you about 10 minutes ago for moderate mitigation, right? So if we do a little bit of mitigation of not emitting as much to the atmosphere, we're going to get warming somewhere from 3 to 4 degrees by the end of this century, right? So none of us is going to be around anymore at that time, but there's a very good chance our kids are still around at that time. Definitely our grandkids are around at that time. And so we don't want to leave them a world that is 3 to 4 degrees warmer. Yeah? The plea of the scientific world has been keep warming below 2 degrees Celsius. Okay. Now, let's move these levers. And it turns out that the people who've put this together, which have been led by the MIT School of Management Sustainability Initiative, they put this together. And this webpage has in the background essentially a math model. And there's thousands of equations in there. Every time we move a lever down here, right? So let's say we improve energy efficiency, yeah? You see that the things on the top moved, yeah? So this is what we started out. We bring this down and up, yeah? Note that by me moving a lever down here, I have actually made a change to this. Now, what was this? Basically, I said that we're going to improve energy efficiency, and that led to a number of changes. Now, our goal, of course, is to keep it below 2 degrees. So now it's your turn. You have all probably heard of what we can do to keep warming the planet to below 2 degrees C. right? There's plenty of things we can do. They are technological, they are political, they're based on taxing stuff. Yeah. Why don't you put a few suggestions and I'll start moving the levers. And we'll see what effect this is likely going to have. So what can we do? You can unmute yourself.
I think there are always improvements in energy efficiency of existing, like we're always going to think we need a bus, we need cars. I think we can always improve on energy efficiency on vehicles.
Yeah. So let's make that a permanent change, right? Let's increase energy efficiency here. Let's say we're highly increased energy efficiency.
That was easy.
Yeah. So it turns out the effect is not huge, right? We only got down 0.1 degrees C here. Yeah. Energy efficiency by itself is not going to cut it. Note what changes. It didn't make a lot of changes to the composition of our energy use. Yeah. We made it just more efficient, but we haven't changed the composition of the types of energy we use, right? We're still using a lot of coal, still using a lot of oil and gas. Yeah? So Nancy suggested, let's reduce coal, right? We could tax coal, right? We could put a large tax on coal. Let's do it. Let's move this all the way, very highly taxed. Okay? Well, that made a bigger change. We're still way not there, yeah? But notice that, yeah, it brings down, but this is the problem with taxes, right? It's not going to be an overnight change. We're going to tax it and it's going to go down, but then you have population keeps growing. And we have a demand, of course, which is not shown here, but there's a graph I could show you with the demand, and that demand keeps going up. Yeah. Let me see here. Energy demand, yeah, let's say coal primary energy demand, yeah, it is going to keep going up. Yeah. All right, that was not let's reset the whole thing here. Let's go back to default, put our energy efficiency, high price of coal, yeah, decrease population. Yeah. Now, that does work. The model only implemented a slight decrease in population growth, and that's because the makers of the model decided that it's not likely that we're going to cut population in half on the planet this century, which would be efficient, right? But it's not very likely to happen. So they basically follow United Nations projections of population development. But yes, that does make a difference, right? I can go back and forth here. It essentially decreases demand, right? So we can make it level off, but we're still at 3.2. So carbon tax, zero carbon, reduce deforestation, right? Good idea. Deforestation is a source of carbon to the atmosphere. Let's do that. That helped a little bit. Yeah, that did help a little bit. Carbon removal. Yeah, so this is called. This is very popular these days. The fossil fuel industry is highlighting that we can do carbon removal at the source, essentially, right? It's called carbon capture and sequestration, CCS. So let's do it. Let's do a lot of it, okay? Whoa, that did actually help, but not all the way, right? It helped quite a bit, right? Let's go back here. 3.1 to 2.7, so that's quite some reduction, right? Where did it happen? Let's look at the left here. Not so much, right? We're still using the same energy sources, right? And it's because this technique is one that is mostly there to remove carbon at the source where we're producing it from the power plants. So it's not actually changing our energy mix. And thus, it's easy to understand why the fossil fuel industry promotes this, right? Because for them, it maintains the status quo, right? For them, it means they can keep using and selling to us, to society at large, the fossil fuels, okay? But from the climate's perspective, yes, it would be helpful if we actually put this in place. We would reduce warming overall slightly. Now, let's see what else I got. Carbon tax and zero carbon, okay? So here is an interesting part. Economists have, in fact, suggested that to implement a carbon tax for a very long time. When I was a graduate student, roughly 30 years ago, this was a hot topic. And it still is today. But unfortunately, only in very few parts of the world has a carbon tax been implemented. So this is down here, carbon price. And let's see what happens when I move that lever, right? So just a little bit. Whoa, I just moved it a tiny bit and it went down 0.3 degrees. That is incredible, right? So let's look at the left here, right? What happened? What happened? Well, because the carbon price is on fossil fuels, because they are the source of carbon, it's very effective. It reduces the use of all of the three, yeah? So unlike the technology that removes carbon at the source, right? What the carbon pricing does is it makes it more expensive to use fossil fuels, right? Regardless of the technology to remove it. So
why is carbon price, or how is carbon price different from, oh, that was coal taxing. That was specifically coal, carbon is overall.
Yeah. So carbon price is a more neutral terminology because it can be implemented essentially in two ways. One is a tax. You put a tax on carbon. The other one is what's called cap and trade. It's where you put a cap on the total amount and then you ask industry to trade the permits that you give them. These two are essentially fall under carbon pricing because the effect of them is essentially the same. It's not, there are slight methodological differences in that type of carbon pricing, but the effect is essentially the same. Now, this would be medium, right? So if I increase this over time, wow, this did the trick. So going from no carbon price that, we had some energy efficiency, population reduction, deforestation, right? The biggest effect really with 0.7 degrees here is if I implement a high carbon price. This is really the biggest effect we can have on the reduction. And so you could argue we're done now, right? So give yourself some applause here because you actually managed through your suggestions of preventing the planet from heating more than 2 degrees Celsius. Bravo.
So, but a lot of things would change if you have the carbon tax, right? You'd have less oil, less natural gas use, right?
Yeah.
And you'd have more renewable energy too, right?
And this is the very good observation, Pam, right? So let me go back and forth on that last one here. Notice that the green area is getting larger, right? And all the others go down. We're basically phasing out coal because coal produces so much carbon, that a carbon price will essentially drive out coal out of our energy system very quickly. A tax doesn't necessarily do this as efficiently, right? So we still have a very high carbon tax in this, right? Let me remove this and notice that had zero effect, right? Because it's all in here. It's not actually in there. So the carbon tax, which on a global basis would be very hard to implement. I'm sorry, the coal tax, which would be very hard to implement because coal is a very abundant fossil fuel, right? Carbon pricing is a much more neutral way of doing this, and it does it more efficiently because what you're taxing is not the fossil fuel. You're not picking one fossil fuel. You're essentially picking the fossil fuel's impact on the atmospheric carbon dioxide. That is much more efficient way of doing so. You can do many other things. It turns out that not implementing a carbon price, so see if we can get there without a carbon price. Let's say we increase energy efficiency in buildings. That does have a large effect. We electrify more things, has also an effect. We can do afforestation. brings it down as well. But none of this has quite as much of an impact than killing off the population might help. Yeah, but we don't want to do that. Yeah. So carbon pricing is much more efficient. We can, even if we if we subsidize renewables, which is one of the things, and that helps, doesn't quite get us there. Yeah. One of the last things I want to highlight here is that if we don't do the carbon pricing, and in fact, it's going to be very hard to get this implemented, we have to do a lot of other things. And specifically, one thing we have to do is we have to deal with other greenhouse gases than just carbon dioxide. And one of the biggest problems is methane. You may have heard that the gas and oil industry in Texas and elsewhere is a big source of methane to the atmosphere. So we can achieve the 2 degrees without a carbon price, but we have to do methane. See, when I do the methane removal, I can get below 2 degrees, even without a carbon price. But I cannot really get there unless I do that. So the greenhouse gas emissions have to drop very rapidly, but they will really drop the most if I also tackle methane and not just carbon dioxide. So
could you mention the political realities and challenges of communicating to policymakers the impact of carbon tax? Do you think they know what's happening now? I suspect those in the Green New Deal have some knowledge. What about the rest of the crew?
Yeah, so for the longest time, actually, the left has advocated something that was invented by the right. The carbon tax, in fact, is not a liberal invention. It is, in fact, a conservative invention, right? The most prominent example is the cap and trade scheme that was implemented by the first Bush administration in 1991 to reduce sulfur dioxide emissions from power plants, which was implemented in order to reduce what was then known as the acid rain problem. Okay?
I remember that. Yeah.
Yeah. So the Bush administration implemented a price on those SO2 emissions. And they did it in the form of a cap and trade program. And it worked beautifully. It reduced by a factor of 10 over the next 20 years. So between the early 1990s and about 10 years ago, the SO2 emissions went down by a factor of 10. And we're not really dealing with an acid rain issue very much longer in the US. We still have a small problem, but it's basically under control now. And so this was a measure implemented by a conservative government and supported by that government because conservative economists told them that this would work. It was a market-based mechanism. So is other carbon pricing, whether you do it as a carbon tax or as a cap and trade program. Now, it turns out that the conservatives have changed a lot in this country. They have not changed much in the rest of the world. So this is a measure that has been promoted in other countries by their respective conservative parties. It's not been promoted by a majority of conservatives in this country, although there is a growing group among conservatives that are trying to convince their party that carbon pricing is what is needed. You may have heard of them. They're called Republic EN. They are led by Bob Inglis, a very socially conservative member of Congress, who was booted from his seat with the Tea Party movement 10 years ago. But he's still very active, and he's trying to convince more conservatives to go tackle the climate change issue through implementing carbon pricing. They have a very straightforward plan. They're very active. They just don't have a majority. It turns out that liberals are actually starting to move away from carbon pricing. And the reason for that is not quite clear. It has been suggested that that is because they've promoted it for a very long time, but it was unsuccessful. So now they're thinking about going back to what they've been accused of doing for the longest time, namely command and control regulation, right? Which of course is going to upset most on the right. So it's bound to remain a political issue for quite some time. What has not changed is the opinion of the vast majority of economists saying, don't regulate, let the market do it, put a carbon price in place. So if you ask 10 economists, 9 out of 10 will tell you, don't do command and control regulation, do carbon pricing. And for the longest time, liberals were behind that. A growing majority among liberals is not behind that anymore. And as I said, it's a bit of a mystery why not.
What does do carbon pricing mean, if not like intentionally driven?
I don't understand the question.
It sounded like when faced with either a regulator saying we're going to implement these changes versus the market telling what the carbon pricing will be. And I'm thinking about your graph here and how we can get down to 2 degrees. What would cause such a change if not some regulation or some intentional intervention like that?
The idea on the right is that putting a regulation in place means that you're dictating to the emitter what to do.
Yeah, nobody likes
and
that.
that is and they don't want that, right? They are much more open to the idea that putting a carbon price in place and then let the market decide the most effective way of reducing the carbon. So in other words, you don't dictate to everyone what to do, but you're saying, okay, I'm going to put a cap on how much you as an industry are allowed to emit. And now I'm going to give you paper permits, and you can trade them among yourselves such that the place that has the highest emissions and where you can most efficiently reduce them will do it first.
Yes.
And we know from the past that this typically works well if you implement it well. You may not, or may not, I don't know if you know this, but the Europeans actually tried to implement a cap and trade program 15 years ago, and it didn't work. And the reason was that they didn't get the boundaries right. So they had they put a very high cap in place, and essentially they the price of the permits collapsed. Yeah. So when you do a so-called cap and trade program, the government still sets the boundaries of it. You know?
Right. Okay.
And the market happens within these boundaries. But if your boundaries are too wide, your market is dysfunctional. And so that's what the Europeans learned the hard way. Yeah. They have now learned, and so what they did was they put the boundaries in a more tight squeeze, so to say, and the market seems to have reacted to that. The price of these permits has gone up, and once you have a reasonable price for carbon emissions, the market actually works, and the emissions are driven down. So that is one of the carbon markets that already exist on Earth that seems to be working. Another one is in Canada, not of all Canada, but British Columbia has a carbon tax in place, and it has worked. The last 10, 15 years have shown that emissions of British Columbia have actually gone down as this carbon pricing market is working. The other place of all places that is going to have a carbon market is China, right? You know that China is the biggest carbon emitter on Earth right now. And it turns out it actually has started putting a carbon market in place. Now, it is obviously not the type of market as we think of in the Western world, right? It's a dictated market, basically. But the idea is that the Chinese government dictates how much carbon will be allowed, and it gives its emitters permits. So it's a cap and trade scheme. And the idea is that over time, this is going to drive emissions down. So, it's essentially one of the Chinese created markets. We'll find out, right? Within the next few years, we'll find out how they're going to do it and whether it's going to work. I will not make a prediction.
I was wondering what examples are of the carbon removal and how effective that can be, and is it going to be done more commonly?
Yeah. So what we're talking about is that lever on the right. You can still see my screen, right? With the thing, right? So notice that, if we go from 2.7 to 2.2 or so, right? So this can be, from a climate perspective, this can be quite efficient if you implement it globally, right? So this is a global model. I should have said that at the beginning. This is not US specific or anything, right? So you have to implement this globally. Now, what the model does not do here, or better say it's hidden, you don't see that, is how this is going to be accomplished, right? It turns out that you need to invest a lot of money to make this technology happening. And while it is efficient in the sense that it can remove 90% of the carbon emissions from a power plant, it only works for what we call stationary sources. So in other words, power plants for the most part. So it cannot reduce emissions from cars, for example, right? So unless we change our car fleet to electric, this technology is not going to work on cars, right? It's not something like a catalyst that you can just install. It's actually very energy and financially intensive. And that is the main reason why it has not been implemented already. So what the fossil fuel industry is pursuing or has been pursuing for the last 20 years already, but has not been successful enough at it yet, is that it wants essentially society to pay it to implement this technology to reduce the carbon dioxide emissions, right? They have not been willing to pay out of their own profits to install this, right? And the reason is it's very expensive, right? So it would cut really dramatically into their profits. Therefore, the governments worldwide have implemented a lot of research into carbon capture, but because putting it in place, putting the technology actually at the power plants to reduce the carbon dioxide is expensive, and somebody's got to pay for it. The industry doesn't want to pay itself for it because it would dramatically cut into their profits. So what they're hoping is that basically the political world is going to mandate this and use the money from taxes, maybe a new tax, maybe a tax on carbon, right, to pay for this technology. So this is the general thinking. In fact, I was working for over a year at the research facility for carbon capture in Norway. And the running joke there was among the fossil fuel industry was that first they paid us to dig it out of the ground, and now they're going to pay us to put it back in the ground.
That's a good one.
Yeah. So we may end up there. But the point is, and that was why I was showing you the renewables, massive success of renewables is, if we are in any way intelligent enough, economically and socially, we will not go this route because it's going to be massively more expensive than going the easy route of just installing a lot of renewables. It's going to be so much cheaper. It just doesn't make sense financially to go this technology route. You don't want to do that, essentially. What you want to do is build out your renewables as fast as you can, right? So we can help that through subsidizing and through putting a price on carbon, like I just did here. The quicker we implement this carbon pricing, the more we're going to get that green part here to dominate the system. All right, I talked too much. Need some more feedback from you guys.
No, that was very good. Unfortunately, we have to hear people talk about burn, baby, burn, and that we're called tree huggers and things.
Yeah,
like that.
but you know what? That those voices are loud, but they're now they're not dominant anymore, right? They used to be loud and dominant. Now they're still loud. They're not dominant anymore, and so that gives people like myself, together with these economic and technological developments with renewables, gives me a lot of hope. And I'm looking forward, right? Once it becomes the normal thing to do to have solar panels on your roof, right? The whole thing is just going to take off. I witnessed this in part in Germany when the German government 20 years ago implemented high subsidies for renewables. It didn't matter what you were thinking politically. Suddenly, everyone wanted to have a solar panel on their roof. And part of that is just human nature, right? If your neighbor has a solar panel, the neighbor across the street has a solar panel, the guy down the street has a solar panel. It's peer pressure. Suddenly, everyone wants to have a solar panel. You talk to them and they tell you, well, you know, I'm not paying anything anymore monthly on my electricity bill. It just becomes a peer pressure and it takes off. And if you cannot drive through a single town in Germany anymore without seeing multiple homes with solar panels on their roof. Even my arch conservative father wanted to do it. And the only reason he couldn't was that his roof was so old, it had asbestos in it. And he was just not willing to pay for the remediation of the asbestos, which had to come along with installing solar panels on his roof. So there you have it. But as we turn over our infrastructure, a lot of this is going to become second nature, right? I mean, you see it in town. We're not renovating some of the oldest buildings, right? We're building new. And while most of us don't like the axe shacks that go up everywhere, one thing we have to realize is it houses people, and it's 10 times more energy efficient than that old building that was there. So as we turn over our infrastructure, we're going to do a lot of these things that are I showed you here with this model, just by there's no political incentive of doing it, but we're just doing it because it makes a lot of good sense. So what we need is a little bit of reinforcement of this, right, which comes through economics. It can come through some regulations, right? A lot of drivers of why buildings are so energy efficient these days is because we have architects who have their own, groups, professional organizations that inform decision makers, right? And so we have to thank architects for most of the high energy efficiency we have nowadays, right? Because what you teach in class and you communicate with others in your professional organization, it makes it to the decision makers eventually, and it becomes second nature not to build that house which is poorly insulated, right? We have standards now simply because it makes a lot of common sense to have these standards. We may have to, go a little bit faster pace. And so that is the political part, but it's coming along. Eventually, it's going to happen. It has to happen fast if we want to keep it below 2 degrees. So that is the challenge to all of us, right? We have to try to make this happen much faster than what we are used to. So that is my final message, I guess.
Gunnar, could you put the link to this in the chat?
Yes, very happy to do so.
Thank you.
Let me quickly go to my other screen here, so I can copy it from there. Where is it now? I have to search my own screen here.
I know what you mean.
All right.
Well, it's nice to hear somebody who's positive about global warming.
Yeah. Okay. So the link is, I will send Pamela the slides, and she can distribute those to anyone interested or post them online.
Yeah.
That'll have the link in as well. Yeah, the fascinating thing about this program is you can just go there and play around with it. You can read up on it. It's very well documented. Yeah. I'm sorry?
They're both toured. Close the door.
We need different bands.
I can hear talking, but I cannot decipher what is being said. Oh, maybe that was just all right. So see, when you go over here under simulations, I think I'm still sharing that screen. Yeah. You can reset things, and you can actually read up on this. What assumptions go into this model, and it's all very well documented, right? Fossil fuel utilization. You can go under the different levers here. There's every single one has these dots, and it opens a new window, and it shows you, well, what does highly subsidized actually mean? Yeah. So in this case, it means paying for about 3 cents per kilowatt hour. Now, I showed you before that we actually expect in some places the technology to only cost 3 cents per kilowatt hour in 10 years from now, right? So if you put a subsidy of 3 cents per kilowatt hour up, solar would be for free, literally. So that's what this means, basically. So a lot of these assumptions that go into this are actually very, very reasonable, right? So this is not some hypothetical thing that's out there. Yeah? Scientists, social scientists, and the economists working on this, they have thought really hard about this. So this is not some crazy notion that goes into this, right? This is all very doable, and it could be implemented very, very quickly if we want to. All right. Well, thank you very much for having me.
Yeah, thank you.
You're very welcome.
And keep teaching the undergraduates about this, so maybe the world will change.
Oh, it definitely will. The problem is just pace, right?
Right.
We can speed it up. This is going to be a pat on the shoulder of humanity.
Just more education. All right, thank you. Bye-bye.
Have
Bye,
fun.
everybody.
Bye-bye.
Go out and help someone, it's the best we can do. There's someone who needs someone